Assalamualaikum and hi. In this video, we will discuss metallic bonding and band theory. My name is Nur Kimia binti Kamiruddin and these are my group members. First, we have Nura Zika binti Zahar, Nur Alia Farhana, Putri Nurul Irdina, and Nur Hazira Afika. Firstly, I will explain the objective of this topic. First, this topic aims to explain how metal atoms are held together by a sea of delocalized electrons, which is known as metallic bonding. Next, it describes the structure of metals where positive metal ions are arranged in a lattice and surrounded by freely moving electrons. This concept also helps us understand why metals are good conductors of electricity and heat. Finally, learning metallic bonding provides a basic foundation for studying material science and understanding the use of metals in daily life, such as in wires, cookware, and electronic devices. Next, we move to introduction. Metallic bonding refers to the attraction between positive metal ions and a sea of delocalized electrons. These delocalized electrons are not fixed to one atom and can move freely throughout the metal structure. Because of this strong attraction, metallic bonding forms a strong bond that holds metal atoms closely together. The strength of metallic bonding increases when metals have more valence electrons and a smaller atomic size. This free movement of electrons allows metals to conduct electricity and heat efficiently, which is why metals are commonly used in electrical wiring and cooking utensils.
Hi everyone, now we are dividing into the electron simony. It's a fascinating concept. We will apply four rules to simplify how we understand metal. Take a look at this structure. Imagine metal atom packed as closely as possible. But here's the twist. It's actually a lattice of positively charged ion surrounded by a massive sea of delocalized electrons. Now, why does this matter? Because the electrons are delocalized. They can flow freely through the metal. This free flow is exactly what makes metal malleable and conductive. Think about the device you use every day. The model explains how electrons migrate easily under an electric field, playing a huge role in the electrical circuit that power our world today. But wait, why are these electrons swimming around so free? It all comes down to the chemistry. Valent electrons in metals are held very loosely because of low electronegativity. Basically, the attraction to the nucleus is weak. Because that grip is so weak, the atom basically say goodbye to those electrons, forming positively charged metal ions. Meanwhile, those free out the electrons exist as a negatively charged cloud. And here is the magic word. Electrons are shared by a multiple neighbors. This creates a strong attractive force between the negative cloud and the positive ion. We call this the metallic bond. The best way to remember it, think of the electron sea as a powerful glue that holds all these positive ions together tight.
The band theory of metals is based on the valence band and the conduction band. It is also known as the band theory of solids and zone theory of solids. The energy bands can be classified into three, which are valence band, conduction bands, and forbidden bands. There are two most important bands, which are the valence band. Electrons contains electrons involved in bonding, and the conduction band contains electrons that can move freely and conduct electricity. The energy difference between these bands is called band gap. Therefore, it defines conductors, which is metal, semiconductors, and insulators very clearly and distinctly. Let's take a look at the valence and conduction band. The valence band is the energy band that contains energy levels of valence electrons. This band may be found beneath the conduction band. In addition, the electrons in this band are weakly connected to the nucleus of the atom. It is made up of electron-filled valence shell orbitals. The energy of electrons in the valence band is lower than that electrons in the conduction band. On the other hand, the conduction band contains the energy level of unbound electrons, also known as free electrons. External energy must be applied in a way that the valence electrons push the conduction band and become free for electrons to be free. Conduction band is made up of orbitals in the valence shell and upper empty shell that aren't occupied by electrons. Movement of these electrons results in electric current. The forbidden band, also known as the band gap, refers to the gap between the valence band and the conduction band. Forbidden gap doesn't have any energy or no electron stays in this band. If the forbidden gap is greater, then the valence band electrons are tightly bound or firmly attached to the nucleus. In metals, the valence band and conduction band overlap or the valence band is partially filled. Therefore, there is no band gap between them. Electrons do not need extra energy to move into higher energy states. As a result, electrons can move freely under an applied electric field. Since there are many free electrons available, electrons flow easily when electric field is applied. This explains the high electrical conductivity of metals such as copper, iron, and aluminum. Under low temperatures, metals can still conduct electricity because free electrons are already present. Let's take the example of sodium. Sodium has an atomic configuration of 1s2, 2s2, 2p6, and 3s1. It has 1 unpaired electrons in the 3s orbital. The 3s valence atomic orbital of sodium overlaps with another such orbitals of the same energy to form molecular orbitals. The atomic orbitals continue to combine in some fission, forming a band. The energy spread of this band is calculated as the difference in the energy between the most strongly bound, also known as bonding orbital, and the highest energy anti-bonding.
Metallic bonding is a type of chemical bonding found in metals, where the positive metals ions are held together by a sea of delocalized electrons. These electrons are not attached to any single atom and can move freely throughout the metal structure. This unique bonding explains many important metallic properties. One key application is electrical conductivity, because the electrons can move easily. Metals such as copper, silver, and aluminum efficiently conduct electricity, making them ideal materials for electrical wiring, power transmission, cables, and electronic devices. Metallic bonding also explains why metals are good conductors of heat. When heat is applied, the free electrons gain energy and transfer it rapidly through the metal. This property makes metals suitable for cookware, kettles, radiators, and heat exchange used in homes and industries. Metallic bonding also allows metals to be malleable and ductile. Since the bonding is non-directional layers of metals, atoms can slide past one another without breaking the metallic bonds. This allows metals to be hammered into thin sheets, such as aluminum foil, or drawn into long wires, such as copper wires. Another important application is in construction and transportation. The strong attraction between metal ions and delocalized electrons give metal high tensile strength and durability. As a result, metals like steel and iron are widely used in buildings, bridges, ships, cars, and aircraft frames. Metallic bonding gives metals high durability and toughness. The strong attraction between metal ions and the sea of delocalized electrons allows metals to absorb energy without breaking easily. This makes metals resistant to wear, impair, and deformation. Because of these properties, metals are widely used in machinery, tools, and industrial equipment, where strength and long-lasting performance are essential. In addition, metallic bonding enables the formation of alloys. Alloys are a mixture of metals or metals combined with small amounts of non-metals that have improved properties. For example, steel is stronger than pure iron, while brass is more resistant to corrosion. These alloys are widely used in tools, machinery, medical instruments, and industrial equipment. In conclusion, metallic bonding is essential to modern life because it explains why metals are strong, conductivity, flexible, and durable, making them suitable for a wide range of real-life applications.
Assalamualaikum. My name is Nur Alia Farhana. Today I will talk about semiconductors. Semiconductors have a small energy gap between the valence band and the conduction band, which allows the electrons to move when sufficient energy is applied. Their electrical conductivity is intermediate, meaning it lies between the conductors and insulator. Unlike metals, semiconductors can conduct electricity better at higher temperatures. The flow of electrons also can be controlled depending on how much the amount of energy is supplied. Common semiconductor materials include silicon, silicon carbide, indium phosphide, gallium nitride, and also gallium arsenide. Next, let's move to the type of semiconductors. There are two types of semiconductors, which is intrinsic semiconductors and extrinsic semiconductors. First, for intrinsic semiconductors, it has a pure material without any addition of impurities, and none of doping is done here. Most common element used in these intrinsic semiconductors is a silicon and germanium, since both of these elements is a tetravalent elements. It can form 4 covalent bonds at zero temperature. When the temperature is rise, the thermal energy will break some of the covalent bond and thus release the electrons. The released electrons become the charge carrier and the empty position become holes. In these intrinsic semiconductors, the number of excited electron is equal to the number of the holes. It also have diamond cubic crystalline structure and the Fermi level is moderate. Next, for extrinsic semiconductors, it has an addition of impurities in purpose to increase their conductivities. The impurities or dopants can be either provide more electrons or more holes. In these extrinsic semiconductors, the number of excited electrons is not equal to the numbers of the holes, and the Fermi level is near to the conduction band or valence band. Extrinsic semiconductors is divided to two types, which is N-types and P-types. Since I mentioned many times about doping, so let me tell you what is doping do. So doping is a process where there are impurities added to the semiconductor to improve their conductivity. For N-type semiconductors, it is known as impurities donor. It has the addition of pentavalent impurities, which their atom have 5 valent electrons, such as antimony, arsenic, and phosphorus. These impurities donate extra electron to the semiconductor material and create free-moving electrons that act as the main charge carrier. As a result, these electrons are negative charge carrier and make the semiconductor as N-negative. For P-type semiconductors, it is known as impurity acceptor. It has the addition of trivalent impurities, which their atoms have 3 valence electrons, such as boron, aluminium, and gallium. These impurities leave a hole in the valence band after allowing the excitation of valence band electron. There are several applications of P-type semiconductors. First is solar cells like photovoltaic technology, photodetectors such as sensor and cameras, and lastly a laser diode. Below we have the example of semiconductors. First is the integrated circuit, microchip, transistor, LED, and lastly is RFID.
In conclusion, metallic bonding explains how metal atoms are held together by a sea of delocalized electrons surrounding positive metal ions. This unique structure allows electrons to move freely, enabling metals to conduct electricity and heat efficiently. Understanding this concept provides a strong foundation for material science and helps explain the widespread use of metals in everyday applications.